Hi friends, welcome back in this series of computer vision. So today we have another case study on transfer learning. So as we discussed in the last video, we have worked with a faster RCNN, then we have checked the SSD model, then we tried with YOLO as well. Now we will see how the transfer learning basically works and how we can make our custom model using transfer learning. Before starting, would again request you to please subscribe the channel because we need more subscribers that our team will get motivated from it, and team will keep providing the content related to AI. So before wasting time, let's get started. So the table of content that we are going to see is importing library, then loading the visualization data set, then data exploration and preparation, of course the CNN model. So we will be using transfer learning using VGG16, transfer learning using Resnet, transfer learning using MobileNet, and transfer learning using DenseNet, and finally we'll see some observations. So importing library, again we are using the TensorFlow 2.x version. So then of course, and if we check the version that we are using is 2.6.0. now importing library for data manipulation. So here NumPy is used for large multidimensional array and matrix along with the mathematical operation on these array, whereas Panda is used for data manipulation and analysis. So import NumPy and Panda. Now matplotlib of pyplot, of course, is a data visualization library for 2D plots of arrays and built on NumPy arrays. Now Seaborn is based on matplotlib, so which aids in drawing attractive and informative statistical graphics. So Seaborn as SNS. Now OS, so OS is used to provide a way of using operating system dependent functionality where we are using random pickle, of course pickling our model. Right now sklearn, so yeah, for doing some pre-processing, like we will be using label binarizer, then train tester split from the sklearn, then classification report, then F1 score classification report, and confusion matrix. So all we access it from sklearn. Now library for working with images and CNN, so CV2 as our OpenCV library. Now Google patches, if you are working on Google Colab, so this library will be helpful to show the images. TensorFlow as TF, so tensorflow.keras.model, so of course sequential for our model building. We are including all the layers, and indents, activation, dropout, flatten, convolution 2D, max pooling 2D. Then tensorflow.keras import optimizers. From TensorFlow Keras application we are importing Resnet 50, VGG16, VGG19, MobileNet v2. so we will be using all these models today. Now tensorflow.keras application, Resnet, preprocess input and preprocess res50. So initialize the random number generator. So of course import random and random.seed0, so ignoring the warning. So we normally import warning and do the filter warning as ignore. Now loading and visualization data set, so we are using again CIFAR10 data set, so we can easily access it from tensorflow.keras.dataset. import CIFAR, train x, train y, test x, test y. So CIFAR load data, train x dot shape, test x dot shape. So you can see that it is downloading the data. If we check the shape, so these are train x shape and these are text test shape. Now train y shape, test y shape, so we can see the shape of it as well. Now checking shape and size of the independent variable. So what is our independent variable? So here train x dot shape, you can see here, and shape of test data, test x dot shape. Checking the shape and size of the label data, so this is the train y shape, right? You can see here, and this is test y shape. Now visualizing the images along with their labels. So from CIFAR, what kind of images we have? So here show img count data label, so we are passing these three parameters here. Figure and access, so plt.subplot 1 count fixed size we are passing. For I in range 0 and count, so count basically we will be passing, that is the number of images we want to visualize. So XSI image show data I label will be same, and access I set title. So again the title will be as the title of the data. Now show image 5. So we are calling this function for 5 images, right? Train X we are passing, train Y we are passing. So here we can see we got 5 images. The image 1 as label 6 is not clearly visible for me. Label 9 I can see it as truck. Label 9 is here, label 4 is here, label 1 is here, right? Now data exploration and preparation. So get the count of each label. So train label equals to pd dot data frame, train Y columns equals to label. So we are basically getting all the columns. Now train label dot value count. So you can see that for 9 we have 5000, for 8 we have 5000. We can see that from 0 to 9 we have 5000 images in each label, right? So these classes are equally distributed in the train set. Now standardization. So train X dot shape, test X dot shape. So 50,000 32 32 3, then 10,000 32 32 3. Train X 0 of 0. So this is basically giving the array format. Now scale the row pixel intensitize to the range 0 to 1. So train X standard, test X standard. So train X by 255.0, test X by 255.0. So check few values. So train X standard dot shape. So 50,000 32 32 3. Check few values. So test X standard 0 to 10. So here we got all these in array. Now save encoded target. So from TensorFlow Keras util import to categorical. Now number of classes 10, right? Train Y category. So to categorical train Y 10, and test Y category to categorical test Y of 10. Now printing train Y categorical dot shape. So you can see that we got 50,000 and 10. Then similarly for test Y cat dot shape 10,000 and 10. Now starting with the CNN model. So defining the variable image row 32, image column 32, class is 10, test size is 0.3. that means 30% is test size and 70% is our train size. Now random state equals to 42, right? That is only an integer that we have to pass. Model no epoch. So we have a number of epoch, we are giving 50. That means it will go to the 50 epochs. Batch size 32. That means in one batch. So basically we are passing 32 parameter in one batch. Input shape 32 32 3, right? So model CNN of course sequential, then adding convolution 2D. Model CNN dot add convolution 2D 32, kernel size 3 by 3, activation ReLU, kernel initializer he normal, input shape then model CNN add max pooling 2D layer. So we are adding the max pooling 2D layer. Similarly the convolution 2D for 64, kernel size is again same, and activation ReLU for next layer max pooling layer 2D, pool size 22, convolution 2D, then we are passing the size 128, activation ReLU again convolution 2D 128, activation ReLU, flatten we are calling here, and dense 128, activation ReLU, dropout 0.5, and adding one more, that is dense 128, activation ReLU. If we check the output layer, so here model CNN dot add dense, number of classes, and activation softmax. Now what we can do is first we are checking model CNN dot summary. So here it is showing the summary that just we defined all here. Of course the total parameter, the trainable and non-trainable parameter here. Now initialize the model and optimizer. So you'll want to use categorical cross entropy for multi-class classification. So SGD equals to optimizer dot SGD, learning rate is 0.001, momentum 0.9. Now RMS optimizer dot RMS prop, right? Model CNN dot compile. So loss equals to categorical cross entropy, optimizer SGD, matrix accuracy. Now importing time, start time, time dot time, then CNN history. So model dot CNN dot, now fitting the model on train X standard, train Y categorical. Now batch size, we have the batch size as we have our batch size here, epoch 25, validation data, test X standard, test Y categorical. Now printing seconds. So at last it will show the time. So first it will go up to 25 epochs as we defined here, right? So you can see the validation loss here. Now the second or the time it has taken is 449 seconds to execute the complete model building process. Now result equals to model CNN dot evaluate on test X standard, test Y categorical, print test accuracy result of 1, evaluate the network. So from sklearn dot matrix import classification report and confusion matrix. Prediction equals to model CNN dot predict test X standard, batch size is 32, printing confusion matrix. So test Y categorical dot argmax x is equals to 1, prediction dot argmax x is equals to 1. So again 313 by 313. So here you can see that the test accuracy that we have and the confusion matrix we got. Now from sklearn dot matrix import f1 score. So if we check our f1 score of test Y, prediction dot argmax x is equals to 1, average equals to weighted. So here this is the 73%. Transfer learning using VGG16. So another model we are going to use as VGG16 from transfer learning. So TensorFlow.keras applications import VGG16, TensorFlow.keras layer import input. Load the VGG model image input 32 by 3, then VGG convolution. So VGG16 weighted image net including top false and input shape input image input. So this is what the parameter we have to pass. Now freeze all the layer except for the last few layers, right? So this is how the transfer learning basically works. So for layer in VGG convolution dot layer, right? So except the last 5 layers. Now layer dot trainable equals to false. So creating the model VGG equals to sequential. Add the VGG convolution base model. So model VGG dot add VGG convolution. Add new layer model VGG dot add flatten, model VGG dot add dense 512 activation ReLU. Similarly model VGG dot add dropout 0.5, model VGG dot add dense 256 activation ReLU, model VGG dot add dropout 0.5. Similarly model VGG dot add dense 128 activation equals to ReLU, model VGG dot add dropout 0.3, model VGG dot add dense 128 activation equals to ReLU, model VGG dot add dropout 0.3. Now output layer. So model VGG dot add dense 10 activation softmax and model VGG dot summary. So if we get the summary here, so you can see that we get all that thing that we just defined, the total parameter, trainable parameter and non-trainable parameter this time. Now initialize the model and optimizer. So SGD equals to optimizers dot SGD, learning rate is 0.001, momentum 0.9, model VGG dot compile, loss equals to categorical cross entropy, optimizer equals to SGD, matrix equals to accuracy. So importing time first, again start time dot time, VGG history, model was VGG dot fit, train X standard, train Y category, batch size equals to batch size, epoch equals to 25. So validation data we have test X standard, test Y category, print second, time dot time minus start time. So this is all that epoch we have. So as we defined 25 epochs again, so we can see the time that we got to train this model. So that is 1344 seconds right here. Now results equals to model VGG dot evaluate test X standard, test Y category. So evaluate the network from sklearn dot matrix import classification report confusion matrix. Now prediction VGG equals to model VGG dot predict on our test X standard and batch size is what that is 32. Now the confusion matrix. So of course you can see that the confusion matrix we got in this format. Now transfer learning using Resnet 50. So this is a third model that we are going to see that how it works. So from Keras application importing Resnet 50, right? And then Resnet model equals to sequential, then res equals to Resnet, include top false, weight ImageNet, then input shape 3 res model dot add res, then add new layer. So res model dot add flatten, res model dot add dense 512 activation ReLU, then the dropout 0.5, then next is dense 256 activation ReLU, dropout is 0.5, then next is dense 128 activation ReLU, dropout is 0.3, and the final output layer is that res model dot add dense 10 activation softmax. Now res model dot summary. So of course all the thing that we have just defined we got here: resnet 50, flatten 5, dense 23, dropout 19, dense 24, dropout 20, all that like this, or like that. Total parameter, this one, trainable and non-trainable. Now res model dot compile, loss equals to categorical cross entropy, optimizer equals to SGD, matrix accuracy that we have from tensorflow.keras.application.resnet 50 import preprocess input. Now trainx standard res, so preprocess input trainx, testx standard res, preprocess input testx. Now import time, so start time equals to time.time, res history equals to res model dot fit, trainx standard res, train y category, batch size equals to 100, epoch equals to 25. Now validation data equals to test x standard res and test y category, print second, so last it will print the time after completing all the epochs. So here you can see the loss we got here is 0.0875, the accuracy we have 79%, and the time it has taken to train the model is 948 seconds. So you can see that the time is increased again. Now this is the confusion matrix, so you can see the confusion matrix. So we can plot it very nicely, but since this was trained in Google Colab, but locally if you do in Jupyter notebook by using confusion matrix, it will you can print a nice confusion matrix here as well. Now fourth is the MobileNet. So using transfer learning, again tensorflow.keras.application import MobileNet, mobile equals to MobileNet, include top false, weight equals to ImageNet, input shape 32.3, so class is train y.shape. So here it is taking all these in mobile. Now model mobile equals to sequential, so model mobile, so adding the base model mobile dot adding this mobile that we got from this shapes and all. Now the model mobile adding dropout at 0.5 and doing the flatten here. Now using the new layer model mobile dot add dense 512 activation ReLU, dropout of 0.5, so adding a dropout layer that will randomly drop 50% of the weights, right? Next is dense 256 activation ReLU, next layer is dropout 0.3, then dense 128 activation ReLU, then dropout 0.3. Now finally the output layer, so model mobile dot add dense 10 activation softmax, and if you get the summary you get all these thing into a shape. So the layer, the output shape, and the parameter. So the total parameter we have the trainable and the non-trainable parameter. Now SGD. Now the model mobile dot compile, optimizer Adam, loss equals to cross categorical cross entropy, matrix equals to accuracy. So again using the training part, so importing the time to get the seconds that the model is trained. Now model history equals to model mobile dot fit, so fitting the model on train x train y category, batch size is 100, epoch 25, so validation data equals to test x test y category. So if we see after 25th epoch, so the loss we have the accuracy 80%, right, and the second it took lesser than earlier, that is 459, right? Now evaluating the network, so again printing the confusion matrix for this respective network. Now transfer learning using DenseNet. So here DenseNet is very popular architecture as it gives state of the art results on classification. It also makes use of dense blocks where we connect all layers with the matching feature map size directly with each other. In a dense net, for each layer the feature map of all the preceding layers are used as input and its own feature maps are used as input for each subsequent layer. Now advantage of DenseNet are they attenuate the vanishing gradient problem, strengthen feature propagation, encourages feature reuse, and substantially reduce the number of parameter and computationally efficient. Now DenseNet 169, so from TensorFlow Keras application, importing DenseNet 169. Dense equals to DenseNet 169, input shape 32, 32 by 3, include top false, weight equals to ImageNet. So here length of dense dot layer 595, so model dense equals to sequential. So model dense dot adding this dense as base model. Now model dense dot adding the flatten on that, and the defining our new layers, right? So for 512 ReLU dropout is 0.5, then doing batch normalization here. 256 activation ReLU dropout is 0.3, again batch normalization here, and 128 activation ReLU 0.3, and 128 activation ReLU again 0.3. Now the output layer, so model dense dot add dense 10 activation equals to softmax. So checking the final model summary, so you can see that this is what we have defined: the layers, the output shape, and the parameter, right? Now the total parameter, you can see the trainable and the non-trainable parameter as well. Now SGD equals to optimizer.sgd, learning rate at 0.01, momentum here 0.8, model dense.compile, optimizer SGD loss is categorical cross entropy, matrix is accuracy. Now again doing the time frame, that the taking start time here and doing the end time, right? The current time minus start time, so that will give the time in seconds. History equals to model dense dot fit, train x standard, train y categorical, batch size is 100 this time, epoch is 25, validation data test x standard and test y category. Now you can see that in each epoch the loss that is being decreased, which is good in our case. So here you can see the last we got as 0.1360. the accuracy we have is 79%, and the time it has taken 2564. Evaluating the network, so prediction dense equals to model dense dot predict test x standard, batch size equals to 32. Now print confusion matrix test y category dot argmax xs equals to 1, and predict dense dot argmax xs equals to 1. So here this is what the confusion matrix we got. Inference and conclusion, so we used multiple train inferences and conclusions, so we used multiple pre-trained model like VGG16, Resnet 50, MobileNet, DenseNet, etc. So let's compare the accuracy. So we got these model right in the notebook. So basically we have done like this. Now the model, first we applied CNN, so the train accuracy was 81%, test accuracy was 73%, and time it has taken 7 in minutes this time to train the model. Similarly VGG16 8774 and the time is 20. Resnet Resnet has the train accuracy as 97, test accuracy as 80, and the time it has taken 10. MobileNet 95% as train accuracy, 80% as test accuracy, and 7 it has taken time. Similarly DenseNet 95% as train accuracy, 80% as test accuracy, and time is 15. So you can see the higher accuracy we have is for DenseNet and MobileNet, right? So the highest accuracy for train we have for Resnet, that is 97. The test accuracy remains same 80% for these two as well, but the time it has taken is 10 minutes. But if we talk about the MobileNet, it has taken the lesser time than others, and the accuracy train accuracy was 95 and test was 80. So we can further improve the above accuracy by adding more layers in our models, right, and trying different regularization method, etc. So if you conclude this case study, so we can see that model with the pre-trained architecture have better accuracy but taking more times, right, like this DenseNet and the VGG16, right? So it's a good practice to add a few dense layer on the base model. The uses of appropriate optimizer, epoch steps, numbers are epochs make significant difference apart from the model architecture. So yeah friend, this was all about this video of transfer learning. I hope you have enjoyed it a lot. If yes, please do like and subscribe the channel. That will motivate us, and we will get back to you with the new content in the very next video. Till then, all the best, have a good time, take care.